I will wait for 3 more minutes to get started. Okay. Do you hear me?
Yes. That's
Excellent. Okay. Shall we get started? Is David here? Yes. David, shall I get started?
yes, please. Thank you.
Excellent. Well, welcome everyone. This is the continuation of the lecture this morning of statistical methods in cosmology. So I will continue now introducing some relevant ideas in probability and statistics, in particular those that are relevant for cosmologists like myself. So I will now talk about Bayesian and frequentist interpretation of probability, okay? So there are two different approaches, and basically the main different principal approaches to probability and to statistics. The frequentist interpretation of probability, so there is the frequentist interpretation that defines an event's probability as the limit of the frequency in a large number of trials. So the frequentist defines an event's probability as the limit of its frequency in a large number of trials. Of its frequency in a large number of trials. So, for example, if you're interpreting a probability in a frequentist way, you may observe an event unfold many times, and in the limit, when the number goes to infinity, the frequency of the outcome becomes okay. A Bayesian interpretation of probability, the Bayesian interpretation, is that is based in the degree of belief in a hypothesis and not on a frequency. Okay, so this is based on the degree of belief, and I will explain what I mean by that, of a or in a hypothesis. Okay, so basically, a crucial difference between a Bayesian and a frequentist is that a Bayesian can assigns a probability to a hypothesis. Okay, which is not possible under the frequentist view when a hypothesis can be accepted or rejected. So basically, the frequentist accepts or rejects a hypothesis, but the Bayesian gives a certain degree of probability. So the basic difference is that for a Bayesian, well, actually, let me write it here. For a Bayesian, let me change color here, yeah. For a Bayesian, the data are fixed, but the model is repeatable, okay? So data are fixed, model is repeatable. But for a frequentist, the model is fixed. So the model is fixed, and the data are repeatable. I will explain what I mean by this with an example, okay? So one thing that I want to mention here is that, you know, many people tend to say, oh, I'm a Bayesian, or oh, I'm a frequentist. You know, I don't claim I'm any. I don't think you need to claim you're either a frequentist or a Bayesian. I think the reasonable thing to do is that depending on the problem, you choose the approach that better fits the question you're trying to answer, okay? So for example, say, I want to give you a Bayesian frequentist example. So say I would like to measure omega lambda and omega matter from supernovae data, okay? Omega matter is the matter density in the universe, as you know, and omega lambda is the dark energy density in the universe. Let's just assume two parameters for simplicity. So what would be the two approaches? Well, for the Bayesian approach, you take some prior, say a uniform prior in omega matter and omega lambda. Then for each model, you compute the likelihood of the data, and you compute the chi-square statistics, for example, you use that for computing the likelihood of the data. And then you will use Bayes' theorem, that I will explain in a little bit, where you assign the probability of the model given the data as the probability of the data given the model times the prior. I will explain this in a little bit. Now, what would the frequentist do? The frequentist could calibrate the statistics by assuming a model. So the model is fixed. You say omega matter is some number, omega lambda is some other number. You run many realizations of your supernovae data for that model, and each realization of the data will give you some number chi-squared, okay? Then you histogram these chi-square numbers, and that will calibrate the likelihood. So then you calculate the chi-square statistics for the real data, assuming the same model, and compare it to the histogram. And this will give you the relative likelihood for that model, okay? And you repeat for each model. Okay, so basically, again, the frequentist has a model that is fixed and runs many realizations of that data. And if you want to compute different models, you just fix the different models and compute many realizations of your data. But the Bayesian does something a little bit different. It is common in cosmology, it is very common to use Bayesian statistics to test models for a fixed data set, okay? And the Bayesian statistics makes use of Bayes' theorem. What does Bayes' theorem say? So Bayes' theorem says the following. It says that the posterior probability of the model given the data is equal to the conditional probability of the data given the model times the prior probability of the model over the prior probability of seeing the data. Let me parse this a little bit, okay? So this is the posterior probability. Is the probability of the model given the true data, okay? M is the model and D is the data. This one is the conditional probability of seeing the data given that the model M is true, okay? Conditional probability of seeing the data given a true model M, given M, okay? This is the likelihood, in fact. This is the likelihood is also not, I don't want to do that, sorry. This is the likelihood is also known as Bayesian evidence. So this is the likelihood. And this one over here is the prior probability of the model, the probability that the model is correct before we see the data. So we may say, oh, I think this model, this parameter should have a uniform prior. Okay, so then you impose a uniform prior there. Or I expect the distribution to be Gaussian for this particular parameter. So here is your prior belief of the model parameter. And this one over here is the prior probability of seeing the data under all models. In general, it's a constant, and it doesn't need to be computed explicitly in many cases, okay? So this is the prior probability of seeing the data under all possible models. Okay. Okay, so this is Bayes' theorem, and we are often interested in the posterior probability of the model given the data, but we can often calculate the likelihood of the data given the model. So we use Bayes' theorem to go from one to the other, to go from the likelihood to the posterior probability. We just make use of Bayes' theorem, and we also use it to compare models, okay? So basically, the posterior probability of the model given the data and the conditional probability of the data given the model are very similar if the data are very informative. Because if the data are very informative, our prior belief on the model or the model parameters will not matter, okay? If the data are very informative, the prior is irrelevant, okay? However, when the data are not very informative, the prior, the choice of prior plays a role, and we have to be careful with what we infer for the posterior probability, okay? And Bayesian statistics is also useful for model comparisons. You can see here, so let's say we have two models. So let me write here, model comparison. Say we have two models. Say we have M0 and M1. These are two models, okay? And we want to compare the posteriors, okay? So then we'll have posterior of M0 given the data over posterior of M1 given the data. You can see that the prior probability of seeing the data will cancel out, and this will be equal to the conditional probability of the data given M0 times the prior of M0 over the conditional probability of the data given M1 times the prior on M1. And this guy over here is known as the Bayes factor. Is the ratio of the Bayesian evidence. This guy is known as the Bayes factor. In general, it's written like this, E0, 1, and this is. So the base factor gives the factor by which the relative odds between the two models have changed after the arrival of the data. You see, before we had this belief on the prior belief of model 1 and model 2, but after the arrival of the data, the base prior tells us how that belief changes in order to get the posteriors, the ratio of the posteriors. So the relevant quantity to update our state of belief is the base factor. So if we are trying to find the best possible model that fits the data, and we are doing, say, a Markov chain Monte Carlo likelihood analysis, and we are moving along the likelihood, the best way, and I will explain how we do a Markov chain Monte Carlo if we have time, which I think I will, but the best way in order to update the likelihood is to use the base factor. Any questions about this? No?
No.
Well, okay. If there are no questions, I will continue with the next topic in this course of statistical methods. I see a yes here. Is there a question? John Aremu. Yes, you can speak.
Oh, yes. Thank you very much. Can you hear me?
Yes.
Oh, good. Based on this information that you spoke about the Bayes theorem, is it the same? You were mentioning something about the Monte Carlo um, simulations and all of that. So what I'm trying to ask is how the relevance, like the application of this particular one in these Monte Carlo simulations. I really want you to expatiate a little bit on that before you move off.
Can you repeat? Can someone repeat the question? You want to learn about the application of Bayes?
The application of this particular Bayes factor that you wrote, and the Monte Carlo simulations, or the Monte Carlo proposal that you talked about. I want you to speak more.
Okay. So you're saying, how do we apply the Bayes factor in Monte Carlo?
Yeah,
Yes,
that's
yes.
the question.
Excellent. So we will see in when I explain how a Markov Monte Carlo in the next hour, I will explain this. But we will see that basically I move over parameter space. Okay, so I calculate the likelihood at this point and at this point in parameter space, and then I will take the ratio of the likelihoods, which is this Bayes factor. And if this ratio is bigger than 1, means that the new model, I mean, if the new model is more likely than the old model, this ratio is bigger than 1. So I will move. And if not, I will proceed in a certain way to decide whether I move or not. But it will help me. A Markov chain Monte Carlo likelihood analysis is a way it's a technique to map the likelihood of a particular model given the data. And in order to do that, we will decide whether to move or not in parameter space, and we will use the Bayes factor for that decision because we will want to climb up the likelihood. Is that answering your question? John Aremu, you can talk to tell me if that's answering your question.
Yes, Ansari said yes.
Okay, excellent. Okay, let me continue. So the next topic that I want to talk about is the likelihood. Finally, I have been talking about the likelihood, but not as a full topic, okay? So let me start by saying that while the cosmic microwave background temperature distribution is nearly Gaussian, the distribution of the power spectrum of the temperature fluctuations, the CLs, is not. And high L, the central limit theorem, will ensure that the likelihood is well approximated by a Gaussian, but at low L's, this is not the case, okay? What is the central limit theorem? Okay, so let me talk about the central limit theorem, actually. So the central limit theorem, which is something that we not only use in cosmology, but I would say in most sciences, okay? What it says is that if I have n independent and identically distributed random variables, so I have x1, blah, 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 until xn random variables, they are independent and identically distributed, then the central limit theorem says that as the sample size increases, the distribution of the arithmetic means of these variables approaches a normal or Gaussian distribution with mean, so as n goes to infinity, I mean, not goes to infinity, but when n is very big or large, n is large, then the distribution approaches p of x, goes to, approaches a Gaussian distribution, okay, with some mean and some variance, okay? And when that happens, we can express the likelihood as a Gaussian, okay? So for example, we want to express the likelihood of the temperature given some theoretical CLs. Then if we want to express it as a likelihood, this will be e to the minus, minus here, t times s to the minus 1 times t over 2 with some normalization factor, the determinant of s, where t is a vector of the temperature map. CL theory is just the CLs given by some theoretical model, and S is the covariance. Okay, this is the covariance. Okay. Great. So we can write the likelihood that way. Okay, and then we can add the noise to the covariance if you want, but so if you have, say you have just temperature, let me write the expression for just temperature, this reduces to the following. I can write the likelihood, or let me write -2 log likelihood, which is a common expression, so that I get rid of the exponential. This will be equal to the sum over L of 2L plus 1 times the log of the theoretical CLs over the data, okay, plus CL of the data over CL theory minus 1, okay? This is when I replace the measured data in this expression above, the measured data and the signal covariance. There is a question here. Gaussian distribution is the same as normal distribution, right? Yes, right. When I say normal or I say Gaussian, I mean the same thing. Okay, so if I have, let me see more questions. No, just the thumb up. If I have a lot of modes that are measured in the sky, it is a good approximation to think about the central limit theorem. So I can think of those modes as being Gaussianly distributed, and the central limit, because the central limit theorem applies, and I can write the likelihood as a Gaussian. Sometimes this is not the case. And, you know, for very large patches of the sky where the modes are large, I don't have as many modes. So the Gaussian, the likelihood is not distributed in a Gaussian manner. So then I need to do something else. I cannot use this approximation. Okay, so one way in which I can compute the likelihood, for example, using machine learning, is using normalizing flows to test you know, if I know the likelihood is not Gaussian and I cannot make that approximation, or I can just compute it, you know, using Gibbs sampling in different ways. But this is an approximation only, but we will work with this approximation because, you know, just to start with and to make our lives a bit simpler. And since we are, we have a few hours and we are writing things up, I will continue with this. Now I want to jump into the core of this mini course that I'm giving here, which is modeling of the data and statistical inference, okay? So let's talk about statistical inference. And this is actually statistical methods in cosmology is the name of this mini course. So statistical inference. Excellent. So, given a set of observations, often what we want is to fit a model to the data where the model is defined by a set of parameters. Okay, so say the model is defined by parameters that I will call alpha. Okay. Then what we want is to define a merit function, basically that measures the agreement between the data and the model, okay? So I will adjust the parameters of the model to maximize this agreement, and the best possible agreement gives us the best fit model, right? Now, what should I expect from a fitting procedure? Basically, what I should expect from some statistical method procedure to evaluate my data is to get the best fit parameters, to get some error of the parameters, and a statistical measure of the goodness of fit, right? With those things, I think I would be satisfied. So I want the best, in general, for any data set, not only in cosmology. In general, I want the best fit parameters of my model. I want the errors on the parameters. And I want a measure of the goodness of fit. Goodness of fit, okay? So one could ask, given a set of parameters, what is the probability that the data has occurred? So if I start with a set of parameters for a given set of parameters, what is the probability that the data has occurred? And this is exactly this factor over here that you can see. Let me point it out over here. This is called the likelihood, okay? This guy over there, let me take it out for later when I give you my lectures, but this guy over there is known as the likelihood, okay? And I can get the best fit parameters by maximizing the likelihood, okay? So these, the best fit parameters, I get them back by maximize the best fit parameters, maximize the likelihood, okay? Now, I could use, you know, the likelihood to draw confidence level regrets. You may see this in cosmology, you may also see this in particle physics, for example. Let's say that let's talk about the following. So let's say that DI are our data points, okay, data points. And let's say that y of xi given alpha is a model with parameters alpha. Okay? The least, if I take into account the least chi-squared, the easiest thing that I can do is to calculate the chi-squared, okay? The chi-square is the sum with some weights, okay, of what? Of the data points minus the model, okay? The model given the parameters squared, okay? Where the weights, you know, the minimum variance weights can be taken to be 1 over the variance of the parameters, okay? So the best fit parameters are the ones, you know, to get the best fit parameters, I just minimize this chi-squared, no? So I take delta d chi-squared, d alpha I is equal to 0. I minimize this guy, and I get the best fit parameters. Okay, that's the best fit. That's just one parameter. Now, if the measurement errors are Gaussian distributed and the model is a linear function of the parameters, then the probability distribution for different values of chi-squared at the minimum is the chi-square distribution for some degrees of freedom, okay? I will say this again. If the measurement errors are Gaussian and the model is a linear function of the parameters, then the probability distribution for different values of chi-square at the minimum is the chi-square distribution for some number of degrees of freedom, okay? And the number of degrees of freedom is the number of parameters minus the number of data points. Okay, so what is the chi-square distribution? A chi-square distribution is given by the following. I have the distribution of y is 1 over 2 to the nu over 2 times the gamma function of nu over 2 times y to the nu over 2 minus 1 times e to the minus y over 2, where these nu are the degrees of freedom of whatever I'm considering, okay? So for a chi-square distribution, the mean is given by the degrees of freedom. The variance is 2 nu, and so on. Everything is defined by the degrees of freedom, okay? And I can define the probability that the observed chi-squared is less than some value as, so the probability that the observed chi-squared is less than some value chi-square hat, this is what? This is, okay, chi-square, the probability that this is less than this value for nu degrees of freedom. This is the gamma function of nu over 2, this value 2, okay? Where this guy is known as the incomplete gamma function. You can look it up, incomplete gamma function. You can look it up in Wikipedia. It's also in Mathematica. Okay. So Q is equal to 1 minus P of chi-square, that of chi-square being less than this value chi-square hat. This is the probability that the observed chi-square exceeds chi-square hat by chance. The probability that the observed chi-square is larger than the value chi-square hat, okay? Now, what is the p-value? The famous p-value that you may come, you may run into. The p-value is the probability of obtaining data if the null hypothesis is true, okay? So for example, if a p-value is, I don't know, 0.02, it says that there is a 2% chance of obtaining the data of obtaining the data if the null hypothesis is true, okay? Is the probably, so in this case, we should probably reject the null hypothesis, okay? So the p-value, the larger the p-value, the smaller the p-value, the more likely that we reject the null hypothesis, okay? Now, it is common that the observed chi-square value holds, okay, even for models that are non-linear in the parameter. Because before I told you that the model has to be linear in the parameters, this is also, it commonly holds for when the model is not linear in the parameter, okay? And the probability Q, which is the probability that the observed chi-square is larger than some value, is of the best fit model gives a measure of the goodness of fit, okay? So Q of the best fit model gives a measure of the goodness of fit, okay? So basically, if Q is very small, probably the model is wrong, right? The probability of that the observed chi-square is larger than some value is very small, so probably the model is wrong. We want to minimize chi-square, okay? Okay, and basically the chi-square by eye, when you hear people saying the chi-square, I'm doing chi-square by eye, the rule is that the minimum chi-square should be roughly equal to the number of data points minus the number of parameters, okay? And well, you can think about different criteria for goodness of fit. For example, the Bayesian information criteria, where you balance the complexity of the model with the goodness of fit. You can think about many different ways in which you can assess the goodness of fit. I think I saw a hand up. Joshua Dakim. Please go ahead. I don't hear you.
All right. Yeah. Can you hear me now?
Mm-hmm.
All
Yes.
right. Thank you so much. So my question is, does the p-value is actually the main determining factor for using the model, or there are other parameters that we also look at too?
Great question. So the p-value is a way in which you can assess whether the model is correct or not. You know, you can also use Bayesian evidence for the model. People use different things for determining whether a model is correct or not. You can compare likelihoods with, you can use a Bayesian evidence to conclude whether a model is better than another one or not. You can use different ways, but the p-value is one of these ways, yes.
Right, thank you.
Yeah, of course. Any other questions? If not, let me tell you about confidence regions, okay? Before I move on to Markov chain Monte Carlo likelihood analysis, which is basically where I want to end, where I want to finish this course. Okay, so confidence regions. Let's talk about confidence regions. Confidence regions. Okay, so it's useful in general to present confidence level limits, okay? You may see this 68% confidence level limit, 95% confidence level limit, okay? So basically, the confidence level limits are a region in some m-dimensional parameter space that contains a certain percentage of the total probability distribution, okay? So you can think about the likelihood as e to the minus chi squared over 2. That's why when I say, sometimes I say that you want to maximize the likelihood. Some other times I say that you want to minimize chi squared, okay? Minimize the chi squared, you maximize the likelihood. And you can use the likelihood ratio, okay? So the likelihood ratio is the likelihood at a particular point in parameter space compared to that of the best fit value, okay? So a model is acceptable or not if, going back to the previous question, you can compare models, you can see if the model is acceptable or not by looking at the likelihood ratio and seeing if it's above a certain threshold, okay? So basically, if I compute minus 2 log likelihood over the likelihood at the maximum point, which is the best fit, okay? This is equal to chi squared minus the minimum chi squared, okay? So minimum chi squared corresponds to the likelihood, the maximum likelihood, okay? So I can compare a particular model with a certain likelihood to the maximum likelihood, and this assumes that the parameters have Gaussian posteriors, okay? I'm using here the Gaussian approximation for the likelihood, which is not necessarily always the case, but let's assume this, okay? So what do I do first? First, I find the maximum likelihood. That gives me the best fit parameters. Then I go down the likelihood until I enclose 68, say 68, let me be precise here, until I enclose, say 68.3% of the total probability, of the total probability. So basically, let's say find A and B such that likelihood of A is equal to likelihood of B, and the integral from A to B of the likelihood, which is the probability of the data given the model, is equal to 0.683 times the full probability. Okay. This A and B, comma B, defines the 1 sigma region, or what is known as the 68% confidence level limit. Okay. Now, if instead of 0.683, you do 95.4%, this defines the 2 sigma region, 99.7% defines the 3 sigma region, and so on. You see, this is what I have. Look, so imagine this is the likelihood, and this is some parameter, okay? P bar, I don't know. And I have this distribution, okay? A normal or Gaussian distribution, okay? So this is the maximum, and I find A and B such that this integral, the integral of that over that area is equal to 68.3%. Or I find, no, I didn't want C and D, so that the integral over that area is 95.4%. Or I find E and F, so that the integral over that area is 99.7%. You see, and those define the 1 sigma region, the 2 sigma region, and the 3 sigma region, okay? And those are typical choices that are used for thresholds. Is this clear? This is an important part of the course. Is this clear? Or is there any question? Yes, that is, oh, it's clear. Okay, awesome. Okay, I want to talk also, before I jumped into Markov chain Monte Carlo likelihood analysis, which is the last part of what I want to talk about. I want to talk about marginalization and combination of different experiments, okay? So let's talk about marginalization of parameters or combination of different experiments. So perhaps we're not interested in all of the parameters at the same time. Perhaps we are interested in just some set of parameters. If this is the case, we can marginalize over the rest of the parameters. And by this, I mean integrating over the posterior distribution. So I can calculate the probability. I can calculate the probability of alpha 1 to alpha j over these parameters, given the data, as what? As the integral over the rest of the parameters, j plus 1 until m, of the probability of all of the parameters given the data. You see, here, this, I'm marginalizing over these parameters. Okay. And so this is marginalization over different parameters, okay? So if you have, you can also combine different experiments. So for example, if you have two different independent experiments, they combine, so this is marginalization. Now, combination of experiments. Another common thing to do is to combine different experiments. Okay. So if you have two different and independent experiments, so if the experiments are independent of each other, okay, I don't know, we are measuring two different observables at two different parts of the sky, then the likelihood is just the product of the likelihoods of the different experiments. So the likelihood is equal to likelihood of experiment 1 times likelihood of experiment 2. I multiply them because I multiply probabilities coming from independent events, right? Of course, if the experiments are not independent, then I have to include the covariance between the experiments, okay? Sometimes I don't want to make the full analysis. Sorry, I see a question, but I will get to it in a second. Sometimes I don't want to do the full analysis of the two experiments. I want to use one experiment as a prior for an analysis with a different experiment. In this case, I can multiply by the prior, okay? Okay, so in this case, what I can do is I use the prior, say with a certain experiment, I measure the optical depth. That's one parameter of lambda CDM, the standard model of cosmology. And with the other experiment, I want to measure the rest of the parameters. Then I will calculate the likelihood of the rest of the parameters, but I multiply by a prior on the parameter that I know. It could be a Gaussian prior with a certain mean, that is the measured value, with a certain error, which is Gaussian or non-Gaussian. I can use as a prior whatever I want, but that's another way of combining different experiments. So I can use the information of one experiment as a prior in the likelihood. Okay. Let me see. Turn out the billion results obtained theorem and likelihood, the method used to select the useful, the few useful results. They use likelihood, they do likelihood analysis, yes. They do likelihood analysis to compute the errors, the parameters. Sometimes they run Markov chains to compute the errors and the best fit parameters, definitely. Okay, so the best fit, you know, the value that they report is the best fit obtained by maximizing the likelihood. Is that the question? Yes. Oh. Okay. Oh, it's coming. Not sure. Where? Okay. And with this, I want to jump to the last topic of this course. Okay. I will explain Markov chain Monte Carlo likelihood analysis, and then I will just take questions from you. Does that sound good? Okay. So what is Markov chain Monte Carlo likelihood analysis? Let me see what this is. Number 8. Awesome. 8. Markov chain Monte Carlo likelihood analysis. It's also known as MCMC, Markov chain Monte Carlo. Okay. What is that? So MCMC is a method to simulate posterior distributions. Okay. You can simulate sampling the posterior given Bayes' theorem. So simulates sampling the posterior, which is the posterior of the parameters given the data using Bayes' theorem. Oops, sorry. These are the parameters. And these are the data points. Okay. What's Bayes' theorem? Bayes' theorem tells us that the posterior of the parameters given the data is equal to the posterior, the likelihood of the data given the parameters times the prior belief on the model over the prior of the data. Okay. So let's say you want to put constraints on some number of cosmological parameters. You can think of cosmology, or you can think about particle physics, whatever number of parameters. We are cosmology. I mean, I'm a cosmology, we're not in cosmology, but I'm a cosmology, so I will think about n cosmological. Say we want to constrain n cosmological parameters. Okay, let's say n is 10, just to say something. For example, n is equal to 10, okay? And let's say that you want each parameter to take m number of values. Each parameter takes m values, just to have a grid, you know, of all possible combinations of parameters. So let's say m is equal to 20, just to say something, okay? This would mean that I have m to the n evaluations to do, okay? But this is, in this case, is 20 to the 10 evaluations to do. Okay. So now let's say for each evaluation, I need to run some Boltzmann solver. I don't know, it could be from a publicly available code, okay, to calculate the observables. Or I would run simulations, whatever. So let's say my code is pretty fast. It takes a few seconds per evaluation, okay? Say I take order few seconds per evaluation. Okay. this means that if I want to do 20 to the 10 evaluations, and each evaluation takes a few seconds, this would take about 100,000 years, okay, to conclude. So it would take me 100,000 years. So basically, if I wanted to start to finish a paper this year, I would have to have a Neanderthal start the chains to make it just on time for the paper to be published this year. Yeah, that's too long. I'm seeing the comments from you. Okay, that's way too long, unthinkable. So in order to avoid this problem, okay, this is obviously a problem. In order to avoid this problem, a Markov chain Monte Carlo likelihood analysis is a very powerful tool to overcome this, okay? MCMCs are a class of algorithms for sampling from probability distributions. And so MCMCs, algorithm that samples from probability distributions, okay? So the state of the chain after a chain, meaning a number of evaluations, you know, after a large number of steps, is used as a sample for the desired distribution. This means that when I run this process, I will tell you the algorithm, but I run this process and I evaluate the likelihood in a particular way, the state of my evaluated steps resembles, so the histogram of evaluated steps resembles the probability distribution, okay? And the virtue of this is that instead of going exponentially, instead of the time going exponentially with the number of parameters, the MCMC goes linearly in time with the number of parameters. Okay, so this sounds like magic. We want to understand it because we are scientists. So let's understand it, okay? So how does the algorithm work? How does the algorithm work? Okay. So we will consider here, there are several algorithms that you can use. You can use nested sampling, you can use the so-called Metropolis-Hastings algorithms. So this is the algorithm that I will explain. This is just one algorithm out of many, okay? But it's the most commonly used. Metropolis, and different types of problems, you know, benefit from different types of algorithms. Metropolis, Hastings algorithm. Okay. The algorithm basically draws samples from the likelihood, okay? The sample is then accepted or rejected. So basically we compare some sample, we will compare point X prime in parameter space. I write it as a vector because it's a vector of parameters to the current state, to the current point X, where I'm sitting right now, and I have a ratio of likelihoods, right? The ratio is given by the likelihood for my new point in parameter space over the likelihood at my current point where I'm standing in parameter space, okay? Now, as I was saying before, if this ratio is greater than 1, then I move to the point, to a new point, okay, in parameter space. I mean, omega matter is 0.2, omega lambda is 0.3. That's a point in parameter space, okay? The parameters have certain values. So I move to a new point where my new point is equal to the point that I just evaluated. But if the ratio, if R is less than 1, then I do the following. I draw a random number a random number alpha from a uniform distribution, from 0 to 1, okay? And now, if alpha is less than the ratio of likelihoods, then I move to the proposed point. Okay, this means that, okay, the ratio was not very good, but it's better than just a random number, so I move. However, if alpha is greater than the ratio, then I don't move. I stay where I was, and I try again a different point, okay? And you can mathematically prove that this algorithm converges to the true likelihood distribution. Meaning, if I continue doing that and moving in parameter space in this way, the histogram of all my samples will be the true likelihood distribution of the problem, okay? So the MCMC is a fantastic tool that allows us to make parameter inference using Bayes' theorem in a reasonable amount of time. And I will use Bayes' theorem for the MCMC, okay, to draw the posteriors of the parameters. And so in practice, you know, there will be a lot of things that I have to think about. For example, things to think about when running an MCMC. And these are things that I give to my students in my cosmology course here at Harvard to think about for a final project. I have different final projects. One possibility is to build your own MCMC using a publicly available data set. You guys can do it if you were willing to do it. You can play around building your own MCMC with the algorithm that I just defined. You don't need more than that. And you can see, for example, if you can recover the posteriors from the Planck collaboration using publicly available data. So things to think about are the step size. How do I move in parameter space? You know, you don't want to make it too big. You don't want to make it too small. You can use a proposal density to move in parameter space in a smarter way, taking into account correlations between parameters. You can think about the parameter choice that you're making to ensure efficiency of the choice of parameters. There is also, you know, you can think about convergence. You have to think about convergence of chains. When do you claim convergence of chains? And this is a whole topic, you know, you can read Gelman. I will not go into these details, but you can read Gelman and Rubin from 1992. They have statistics that they define to it's called the R-1 statistics to claim convergence for the chains. There is a burn-in period where you want basically to delete the first point in parameter space to so that the system doesn't retain the memory of the initial point, which is a random choice that you made. And there are many other different details, really, but the algorithm is the one that I just gave you. So with this, I will finish my course, and I am happy to take questions.
Thank you very much, Prof. I think there are some questions in the chat session. I'm just going to read them out. Okay, there's this one from Simeon Taiwo Akinsoya. Okay, there's one from Mba Harrison. For any experiments done, is there any chance of not meeting the algorithm theorem?
What's the algorithm theorem? You mean the MCMC? If it's any, I think what you're saying is there any chance of not mapping the true posterior distribution? Is that the question?
Yeah.
Yes, in fact, and you have to be, yes, okay, I see. Yeah, so many times it's a problem when you have, you could have regions of sometimes you could have islands of likelihood in which you have many different local maxima. And so, you could get stuck at a particular place. The likelihood map could look like this. This is the likelihood, and so you could get stuck at this local maximum, and that would give you the wrong conclusion about your parameters. So yes, it's an art to choose the best algorithm. In those cases, sometimes it's better to use nested sampling algorithm. There are different types of algorithm that are better suited for different shapes of your likelihood. Great question.
Thank you very much. There is this one from Simeon Taiwo. The person said you talked about the maximum likelihood to obtain the best parameters. Are these theorems like the maximum likelihood estimates underlying principles for machine learning algorithms used for data modeling?
That's a great question. I mean, machine learning algorithms are fitting functions, right? Complicated fitting functions, but they are fitting functions. So yes, they do use, they do try to, with the loss function, what they are trying to do by minimizing the loss function is maximizing the likelihood somehow. So yes, they are trying to maximize the likelihood in a slightly different way, right? Not with an MCMC algorithm, but they are trying to maximize the likelihood by minimizing the loss function.
Interesting. Yeah. So the next question, this from John Aremu. This person is saying the Gaussian distribution is symmetric, but the observables in cosmology are not. Is the model used to study cosmology presently adjusting the Gaussian to be asymmetric, or does it make the observable symmetric?
Fantastic question. Many times the likelihood that you use doesn't make the approximation. If you don't make the approximation of a Gaussian likelihood, then, sometimes you can, by the way, you can have a Gaussian likelihood, but the posteriors may not be Gaussian in parameter space. If you do an MCMC and you assume a Gaussian likelihood, you may have posteriors that are non-Gaussian. And so then you don't report a 1 sigma error bar. You report plus minus 68% confidence level region, where the plus and the minus may be different because they are asymmetric. Okay? So the parameters, the posterior in the parameters may be asymmetric. Also, the likelihood may not be Gaussian. And there are ways in which you can, you can avoid making the Gaussian likelihood approximation. But, right. So sometimes people use the Gaussian approximation in the posteriors and in the likelihood in order to make some rough estimate of the error for some future experiment. This is called Fisher analysis, which is used to estimate the errors from a future experiment, but rigorous data analysis will not make use of this approximation. Great question.
Yeah. So there's this one from Pius Prince Wilson. I think he asked 3 questions, so I'm going to take them one after the other. So the first one is, can you please explain the impact of different survey data and their uncertainties on the size and shape of confidence regions in cosmological parameter estimation? That's the first one.
Yeah, I mean, this is a very open-ended question. You can have different surveys measuring different parameters, and so if you measure, for example, you know, parameters, some parameters are not well constrained with certain observables, and some are. So sometimes combining two different ways of measuring the same parameter can reduce the error bar, right? So if you have two surveys measuring, I don't know, imagine you have omega matter, this is omega matter, and a survey that just measures omega matter, this is omega lambda, say. And then another survey that measures just omega lambda, but doesn't measure well omega matter. Sometimes you can combine these surveys to get error bars in the intersection of the two. But, you know, it's not so much about the surveys, but it's about the observable that you're using. Then the other question says, in Bayesian statistics, how does the choice of prior affect the width and locations of confidence regions? Yeah, so if the data are very informative, choice of prior doesn't matter. If the data, that's if the data are very informative. If the data are uninformative, the choice of priors will matter, and sometimes it can bias your results, right? If you put as a prior that the tensor to scalar ratio has to be around 0.4, it will bias your data towards that value, right? Sometimes it can really ruin your estimate. The best thing to do is to put as agnostic priors as you can. So because we want to, obviously we are doing science here, so we want to extract the information from the data, not from our prior belief of the data. Just the choice of word belief already tells you that it's not very scientific. So yes, it can really, if the data are very informative, great case to study. If the data are not very informative, not so good. It means that the error bars will be huge. And if the error bars are not huge, something is going on with your priors, right? How do cosmologists handle covariances between different parameters when constructing confidence regions, and what impact does this have on our understanding of the universe? Yeah, so imagine, I don't know, for example, some surveys, if you were going to take into account two surveys that measure the same patch of the sky, okay, so for example, BICEP and SPT measuring from the South Pole, the same patch of the sky, you should measure the covariance between the measurements, right? The measurements will covary with each other. If one varies, the other one will vary as well, and vice versa. And so that definitely will impact, so the sum, you know, the covariance will impact your measurements. So if you have two very independent experiments, then the overlap, so imagine you have two posteriors coming from two different independent experiments. Then, okay, you know that if these are the two posteriors, the combined posterior will look like this, right? Will look in the region that overlaps between the two. But if the experiments are not independent, they covary, that's not necessarily the case. And so it could go in different directions depending on how the covariance goes, right?
There's another question here.
Yes. So the question is, can you explain in what situations do you use MCMC algorithms over the other algorithms? Yeah, so for example, as I mentioned, I don't know, like when things are pretty, like in the case of Planck cosmological parameters, the Planck results, for the lambda CDM standard model of cosmology measured with CMB, the likelihood doesn't have islands, okay? The likelihood in the CMB doesn't have pocket islands. So you can safely use Metropolis Castings algorithm. But when the likelihood, if you're considering a model, I don't know, for example, a model with features in the inflationary potential, okay? The size of these features could vary over a large range of parameters, and this may have this will have pocket islands with local maxima. So another good algorithm to use in this case is known as nested sampling algorithm, okay? Yeah, so there are different types of algorithms that you can study that are better for different examples, but all of them apply Bayes' theorem, which is the important part, okay? Yeah, so Bayes' theorem, we studied what Bayes' theorem is, and they compute the Bayes factor. And so the Bayes factor may or may not be easy to calculate. You may need to marginalize over nuisance parameters, but you may use different algorithms in order to know when to move in parameter space. When dealing with theoretical models nested in larger models which are underlying to one another, how do you resolve that? What will the first model become an important parameter in the other model? I think if I understand correctly, you're imagining, so this is a question by a person who left the chat, Pius Bamingboye. I think what this person is imagining is having, I don't know, some model with some parameter, and you measure that parameter, and that parameter is embedded in another model that you can measure in some other way. If that's what this person is imagining, I would say that, measuring the first parameter in some way and adding that measurement as a prior for the measurement of the rest of the parameters. I think Pius Bamingboye is online again. So I'm answering to your question. We can think about, again, I think about, imagine you measure some parameter with some experiment, and then you could use that as a prior for the measurement, for the likelihood and the posterior of other parameters using some other experiment. Perhaps that's what you're asking? Yeah. Yeah, okay. Other question. For the Gaussian distribution, you listed it up to 3 sigma. In one of our previous sessions, someone mentioned CERN having to choose 5 sigma detections. Are these X sigma detections related to the Gaussian model? Yes. And does this mean we can have more than 3 sigma? Yes. That's excellent, because in general, cosmologists claim a detection because the data are not repeatable. So we are happy with 3 sigma. It's sociological, this difference, but particle physicists can claim a detection with 5 sigma. So yes, we can have 3, 4, 5, 6, 7, 100, whatever number of sigmas, and that will change the percentage that you are integrating over the total area under the curve. But yeah. Excellent. Are there any other questions? I don't read any more in the chat.
I think that's all.
This is super fun. Thank you. I hope this has been useful. I hope that you learned something today. And if you have questions, please do not hesitate to contact me by email and ask me directly, okay? David? Does that sound good?
Yeah. It's perfect. Thank you very much.
My super pleasure.
Yeah.
Okay, guys, I hope to see you in person someday.
We're looking forward to that too. Will be wonderful. Hopefully the next one.
Have a good night, you over there.
Yeah. Thank you very much, Prof. Thank you so much.
Bye-bye.
Yeah. Thank you very much. I'm going to stop recording.
Awesome. Thank you so much again for the invitation. I will turn off the Zoom now, but my pleasure.
Okay, thank you very much, Prof. Thank you.
Bye-bye.
Yeah. Bye, ma'am. Ooh. Glory to God. I'm going to end it and stop recording. Friends, it's really okay. We're seeing the flex. Where do you?